Hi everyone! Last time we talked about random variables, and we have discrete random variable and continuous random variable. We also talk about, for discrete random variable, we have probability mass functions and the cumulative distribution functions. So for the remaining of chapter 4, we're going to talk about different types of discrete distribution. Today, let's talk about section 4.2, the binomial distribution. So, a typical example is if we flipped the coin 10 times and we want to count the number of heads. Okay, so flip the coin 10 times and we want to count the number of heads. Okay, so let's see the criteria for a binomial probability experiment. An experiment is said to be a binomial experiment, provided it satisfies the following four conditions. First, the experiment is performed a fixed number of times. Each repetition of the experiment is called a trial. So, for example, if we flip the coin 10 times, then we have 10 trials. Okay, so before we start the experiment, we have a fixed number of trials. So for example here, we've flipped the coin 10 times, so that's why this fixed number is 10. Second, each trial is independent of the other trials. This means the outcome of one trial will not affect the outcome of the other trials. And for each trial, there are two mutually exclusive outcomes, success S or failure F. So in our example, if we flip the coin 10 times and we want to count the number of heads, and getting head is the success, getting tail is the failure. Okay, and you can see each flip is independent of each other. Fourth, the probability of success, P, is the same for each trial of the experiment. Because we're flipping the same coin, that's why the probability of getting head is the same in different trials. Okay? Notation for the binomial experiment. N is the number of times a trial is repeated. So in our example, N equals 10. P is the probability of success in a single trial. So it means this is the probability of getting head, okay, in a single trial. So this is like P of getting head. But if the coin is fair, then this P is 1/2, okay? And then the probability of failure in a single trial is 1 minus P, because there are only two mutually exclusive outcomes, either head or tail, right? That's why they are like complement of each other. And then next, the random variable represents a count of the number of successes in n trials. So that's why we can have 0 success, 1 success, 2 success, up to n success in n trials. So okay, so the number of heads, it could be 0. So the number of heads, it could be 0, 1, 2, up to 10 in our example. Okay, so if n equals 1, we get a Bernoulli trial. So we let P be a number in the interval 0, 1, a random variable x with the range of x equals 0 or 1. Okay, so P x equals to 1, so which means we have 1 success. That is P. So the probability of success is P, and probability of failure means 0 success because we only have 1 trial. Okay, so probability of failure is 1 minus P. So then we say this random variable with this probability distribution has the Bernoulli distribution with success probability P, and we denote x has the Bernoulli distribution with success probability P. Okay, if n greater than 1, okay, to denote the probability of k success in n trials. So k success in n trials. Let p be any probability from 0 to 1, and let n be a positive integers. A random variable x with the range of x is 0, 1, to n. Okay, remember, x is like the number of success. That's why the number of success could be 0, 1, 2, up to n. Then this is our notation. So we say this is probability. Okay, p x equals to k, and that, what is that? Remember, we have k success in n trials. So okay, let's say we have n buses. Okay, and we want to pick k of them to fill with success. So we have n buses. We want to pick k of them to fill with success. Okay, and then the rest filled with failures. Okay, then now, so because we have k success, that's why we have p to the k. And because we have n minus k failures, so that's why we multiply by 1 minus p to the n minus k. So here we have n minus k failures. So that's why the probability is this formula. And we can also use the notation b. Okay, so we say this random variable has the binomial distribution with the parameter n and p. So that's why the b stands for the binomial distribution. And you can see k is the variable and n and p are the parameters. Okay, and we denote x has the binomial distribution with parameters n and p. All right. Okay, note. So this is the probability distributions. Probability distributions must satisfy two conditions. First, okay, so this is PMF. Okay, for PMF, we need P of x to be greater or equal to 0, and then the sum of all the x, P of x, should be 1. So this is the criterion for the probability mass function. And now let's see. Okay, you can see here, n choose k is positive, p is positive, 1 minus p is positive, so that's why we have p of x is greater or equal to 0. Okay, and then when we add them all up, what is that? So sum of k from 0 to n, and choose k, p to the k, 1 minus p to the n minus k. Okay, what is this guy? Well, this guy is like when we have k equal to 0, we have n choose 0, which is 1. Okay, remember, n choose 0 equals n choose n equals 1, n choose 1 equals n choose n minus 1 equals n. In general, n choose r equals n choose n minus r. Alright, so this guy is the first guy, k equal to 0. We have this n choose 0 is 1, p to the 0 is 1, and then we have 1 minus p to the n, right? And then we have n choose 1, okay, and then p times 1 minus p to the n minus 1, etc. And then the last second guy, we have n choose n minus 1, and then p to the n minus 1, and this is 1 minus p to the let's see, okay, 1, right? And then finally we have p to the n. Okay, and this is actually the binomial expansion of p plus 1 minus p to the n. So this is the binomial expansion. Okay, so what is the binomial expansion? Okay, I'm going to talk about that later. But now let's continue right here. Do you see P and P cancel? This is just 1 to the n. So that's why when we add up all the probability distributions, we get 1. Okay? So that's why this function P of x, this is really a probability mass function. Okay. And okay, so what is binomial expansion? So here I want to talk about the Pascal triangle. So here I give you a link. When you click this link, you can see this Wikipedia pages. Okay? So Pascal triangle, you start with the triangle. Okay, you put 1 on the side. So we have 1, 1, 1. Okay, and then you have 1. Okay, you add them, you get 2. And then you put 1 on the side, you add them, you get 3. You add them, you get 3, and you have 1. And then this is 4, add them 6, add them 4, 1. Okay, what are these numbers means? Okay, so if you can remember, a plus b squared is what? A squared plus 2ab plus b squared, right? So you can see the coefficient is 1, 2, and 1. So the coefficient corresponds to the coefficients in this row. Okay, next, a plus b cubed. This is a cubed plus 3a squared b plus 3ab squared plus b cubed. And the coefficients corresponds to this row. And in general, a plus b to the 4. Now you can look at these coefficients. You have a to the 4 plus 4 a cubed b plus 6a squared b squared plus 4ab cubed plus b to the 4th. Okay, so the coefficient, the numbers in the Pascal triangles corresponds to the coefficients of a plus b to the n. Okay, and in general, how do we think? How do we get this? How do we get this coefficient? Well, actually, let's look at this one. How do you get this? Well, you're using a plus b times a plus b, and then you have a times a is a squared, and then a times b is ab, and then you have b times a, and then you have b times b is b squared. And because ab equals ba, that's why we have the 2. Okay, so in general, we start with so a plus b to the n. In general, we start with the first term a to the n. Okay, and then the next one, well, we want to have 1a and n minus 1b. So, but you can imagine it's like we have n boxes. Okay, and we want to pick one of them to fill with the a. So that's why we have n boxes. We choose one to fill with the a. Okay, and in this example, because we have 2 boxes, we want to pick one of them to fill with the a. That's why we can have the a is here or the a is here. That's why we get 2. Okay, but in general, we have n choose 1. Okay, next guy, it's gonna be a squared b to the n minus 2. And then, so we have n boxes. We want to pick 2 of them to fill with the a. So that's why you have this. So keep going. Okay, a to the n. So do you realize that this number and this number match? Okay, so that's why if this is n minus 1, then we have n choose n minus 1. And then b, you can see the sum of the degrees always equal n. So that's why here this is b to the 1. And then the last guy we have n choose n, which is 1, and then a to the n. Oh, sorry. Sorry. We have b to the n. Ooh. Oh, okay. I was wrong. I think I have it flipped. So let me fix it. Okay. I think so because we start with a to the n, then we want to decrease the a, increase the b. So here, decrease the a, increase the b. So here, decrease the a, increase the b. So b to the n minus 1. And then this is b to the n. Okay, so now they match. So then this is the binomial expansion. Okay? And now we use this formula and we let a be p and let b be 1 minus p. Okay, so this is the binomial expansion. Oops. Okay, binomial expansion. And we plug in a equals p and b equals 1 minus p, then we can get this. Alright. So if you have questions, feel free to ask me, and here I provide you the link here. You can feel free to go to this website and read more about it. Alright. So now we talk about the Bernoulli distribution. Bernoulli distribution is really like a special case of the binomial distribution with n equals 1. Okay? Alright, couple remark. First, so if x1 xn has the Bernoulli distribution and they are mutually independent. Mutually independent means if I pick any pair of them, they are independent. Then we define x be the new random variable to be x1 plus x2 plus plus xn. This guy has the binomial distribution with parameter n is the number of trials, p is the probability of success. Okay, in second remark, the range of x is usually not S. Okay, so for example, when we have x1 xn be the Bernoulli distribution, random variable, and let x be the sum, and then this guy is the binomial random variable, has the binomial distribution. Then we have the sample space is actually 0 or 1. So 0 success or 1 success, and we have n trials. And the range of x is because we can have 0 success, 1 success, at most n success. And you can see they're different. Oh, by the way, we can also express this as x1 xn and xi are the numbers in 0, 1. Alright. And so what is the size of S? Okay, because each trial we have either success or failure. So we have 2 outcomes in each trial and we have n trials. So that's why 2 to the n. Alright, so let's look at example 1. 60% solar heat installation reduce the utility bill by at least 1/3. Find the probabilities that the utility bill will be reduced by at least 1/3 in 4 out of 5 installation. Part B, at least 4 out of 5 installation. Okay, so here 60%. installation. Okay, so this is probability of success, which is 0.6. Okay, and actually this 1/3 is we're not gonna use the 1/3 here. This is just like success. Okay, the success is we can reduce the utility bill by at least 1/3. So this is the success. All right, now okay, let's look at part A. 4 out of 5 installation. So it's like we have 4 success in 5 trials. So K is the number of success, that is 4. N is the number of trials, which is 5. Okay, and then we have P is 0.6. Now we are looking for P of X equals to 4. Our formula. So we have 5 trials. 4 of them is success. So that's why 5 choose 4. And then success probability is 0.6. And we have 4 success. The failure probability is 1 minus 0.6, which is 0.4. And then what is the number of failures? So we have what? 5 minus 4, which is 1 failure. Okay? So what is that? Well, 5 choose 4. Remember that n choose 1 equals n choose n minus 1 equals n, right? And n choose r in general is equal to n choose n minus r. So 5 choose 4 is the same as 5 choose 1, which is 5. So 5 times 0.6 to the 4th times 0.4. And what is that? Okay, calculator. So let's see. Okay. Let me make it smaller. So we have 5 times 0.6 to the 4th, and then times 0.4. The answer is 0.2592. 0.2592. So please keep your answer in 4 decimal places. Okay. So part B, at least 4 out of 5 installations. So at least 4 means greater or equal to 4. Okay. So I hope you're okay with this. So at least 4 means greater or equal to 4. At most 4 is less than or equal to 4. Right. Okay. So at least 4 out of 5 installations. Well, this means it could be 4 installation or it could be 5 installation, right? So 4 installation, we already figured out this is 0.5. From part A, this is 0.2592. Okay, now 5 success out of 5 installation. So 5 choose 5 is 1, and then we have 0.6 to the 5th, right? And we have all success, we don't have failures. So let's see, what is this? So we can put answer plus 0.6 to the 5th. Oops, I want to press plus, not multiply. Okay, so 0.33696. Okay, so this is example 1. Okay, so once we figure out this is binomial distribution, then we can use the binomial distribution formula to compute. Okay, remember we have a fixed number of trials, and each trials are independent of each other, and each trial we either have success or failure. Okay, next, the cumulative distribution function of binomials. Okay, so the probability mass function for the binomial distribution, we use small b to denote. And so the cumulative distribution function, we use capital B to denote. So that's the probability x less than equal to k. So that is we add the probabilities for I start from 0 up to k. Okay, so that's the probabilities less than equal to k. Alright. Okay, fact. So small b of k and p equals capital B of k and p minus capital B of k minus 1 and p. Why is that? Well, this is x equals k. This is probability x less than equal to k. This is probability x less than equal to k minus 1. And so let's see. So let's draw a picture here. So this is a k. This is k minus 1, right? So that's, yeah. So the probability at x equals to k, that's the probability of x less than equal to k minus the probability x less than equal to k minus 1, right? Then we just have this guy. Okay, and we defined b of minus 1 and p equal to 0. Because we can plug in k equal to 0, then k equal to 0, we define this to be 0, then we just have b of 0 and p equals capital B, 0 and p. Alright. Okay, so now table 1, page 505 in your textbook have all the cumulative distribution function values for binomial distributions with n is less than or equal to 20. Okay, so let me show you. Okay, so on our website, I also provide you here. Do you see the stat table here? The stat table? Okay, so when you click this stat table, then you get this. So I just scanned your textbooks. Okay, now you can see table 1 is the binomial distribution function. So this is the CDF for the binomial distribution, and we have the n values, and then x is the number of success. Okay, and then we have different p's. So n goes up to 20. Okay, so if n is greater than 20, you cannot use the table. Maybe you can use some online calculator or Excel. Alright. Okay, so important thing for the binomial distribution, we can use two ways to compute. The first way, we can use the probability mass function to compute. The second way, we can use the CDF to compute. Okay, so for the PML, I already showed you, we can use the formula, right? This is the formula. And then for CDF, okay, how to compute? Okay, for example, our last example, part A, right? We want to find B of 5.6. Well, this is capital B. So this is the 4. How do we get 4? It means we can use 4 minus B of 3. Right? Because how do you get 4? Well, you use the 4 less than or equal to 4 minus less than or equal to 3, then you can just get P of x equals to 4. So what is this? Okay, let's check out our table. N is 5. So N is 5. So N is 5. Okay, you can see the 5 here. And so let's see. In 4. So x is 4 and p is 0.6. Okay. Can you see x is 4, p is 0.6? Do you see this 0.9222? Do you see this 0.9222? Alright, so this is 0.9222. Minus B3 5.6. So okay, right here, x equals to 3, p is 0.6. Do you see 0.6630? minus 0.6630. Okay, now let's see. So calculator right here. So 0.9222 minus 0.6630. We get 0.2592. Oh, right. Do you see what happened? Oh, you see they're the same. Okay. Okay, how do we compute part B then? So, how do we compute part B? Part B is P of x greater or equal to 4. So, at least 4. Alright? So, if we want to use the CDF to compute greater or equal to 4, so because CDF is less than equal, so we want to change to less than equal. Okay, so we can consider its complement. Its complement of greater or equal to 4 is less than 4, right? And less than 4 means it's less than equal to 3. See, less than 4 is the same as less than equal to 3 because this is discrete. Okay, so now, less than equal to 3, this is the same as B 5.6. And we already figured out this is 0.6630. Okay, 1 minus that. We get 0.337. And I did the same. Yes, close. Okay. Yes. So these are the two different ways we can find binomial distributions, computed binomial distributions with PMF or CDF. All right. Let's continue. Example 2. The probability of certain wide flange column will fail under a given axial load is 0.05. Find the probability that among 16 such columns, at most 2 will fail. Part B, at least 4 will fail. Okay, let's see. Here, P is 0.05. What is 16? 16 is the N. N is 16. Okay, A. At most, 2 will fail at most. So, which means less than equal to 2. Right? At most, less than equal to 2. Oh, right. Oh, and in general, so I suggest you to use the CDF to compute. Okay? Because you can imagine CDF, what you do is you just find the numbers in the table, and then usually you just subtract the numbers. Okay, subtract the difference of the different numbers there. So the operation is easier. But if you want to use the PMF, the formula, you have to compute the combinations and the powers. Alright, so I suggest you use the CDF to compute for the binomial distribution. Okay, what is this? Wow, this is exactly the CDF. So this is the CDF of 2, and then N is 16. P is 0.05. Okay, let's find our table. Here, N is 16, so let's see. Okay, let's see. Okay, 2, no. 16, okay, 16 right here. And P is 0.5 right here, right? So, and X is 2, so you see 0.9571. So, this is by the table 1. Okay, so of course, if you want to compute using the PMF, you can still do it. You can, but to compute the PMF, you have to do, what is P of x equals to 1 and what is P x equals to 2. See, you need to compute both of them and add them up together. Okay, and let's continue. So part B. Part B, at least 4 we found. So at least 4, which means x is greater equal to 4. Okay, greater equals, because CDF is less than equal. When you see greater than or greater than equal, you kind of think about the complement. So the complement is less than 4. Well, less than 4 means what? So let's say this is 4. Less than 4 is the same as less than equal to 3. Right? Less than equal to 3, then this is B of 3 and 16 and 0.05. Alright, what is that? This guy, 9930. Alright, and so 9930 is just 0.007. Okay? So this is part A and part B. Okay, let me ask you more questions. Let's do part C. Find the probability of, let's say we have 3 less than equal to x less than 7. So if we have this, what happened? Well, okay, in general like this, you want to look at, okay, 3, you want to draw the real number line. 3, you want to include the 3, and 7, you don't want to include 7. That's why you want to have less than equal to 6 minus less than equal to 2. You don't want to minus less than equal to 3 because you want to have the 3 stay there, right? So that's why this is Px less than equal to 6 minus P of x less than equals 2. So this is B6, 16, and 0.05 minus B of 2, 16.05. Alright, so what is that? Oh, you can see 6, we get 1, and 2 is 0.9571. So 1 minus 0.9571. The answer is 0.429. Oh, 0. Okay? So this is how we can use the CDF to compute. And you can see why CDF is easy, because you actually, given any range, you just want to figure out this is the difference of the two numbers from the table. Okay, but if you want to use the PMF to compute, well, then you have to figure out, oh, okay, this is x equals to 3, and x equals to 4, x equals to 5, and x equals to 6. See, we have a lot. And then for each of them, you have to use the formula to compute. So that's why, in general, use CDF is easier. Okay? Alright, so let's continue. Example 3. According to the Higher Education Research Institute, 55% of college freshmen in a 4-year college and universities during the 2003 were female. Suppose 10 freshmen are randomly selected and the number of female is recorded. Part A, find the probability that exactly 7 of them are female. Part B, find the probability that fewer than 3 of them are female. Part C, find the probability that at least 3 of them are female. Okay, so this is a binomial distribution, right? So here, 55% of the college freshmen were female. So this is P of success. So in this example, success is females. So success is really like what we're interested, we want to know. Okay, so success could be something bad, because for example, if we want to find the number of defective products, Okay, let's say a factory produce some products, and the percentage of defective is like 10%, and then success is defective. So success is not always good things. It could be bad things like defective. It's just something we want to know. Okay, then we define it to be success. Okay. All right. So probability of success in this case is 0.55. All right, and suppose 10 freshmen are randomly selected. So n equals 10. Okay, so part A, find a number that exactly 7 of them are female. So probability x equals 7. Well, x equals 7, you either use the PMF or use the CDF. So I suggest you to use the CDF. So from now on, when we see the binomial distribution, if n is less than or equal to 20, we can use the CDF to compute. Okay, 7. How do you get 7? That is less than equal to 7, subtract less than equal to 6, right? So this is less than equal to 7 minus x less than equal to 6. And this is the 7 and n is 10, probability 0.55. 6, 10.55. Alright, let's see. Okay, n is 10, so 10, where's 10? Right here. Okay, so 7, right here, 0.55, so this is 0.55. So you see 0.9004. And what is the probability of 6, 10.55? It's the same column, we just go up one entry. So 0.7340. Okay. Alright, what is that? Okay, where is our calculator? Let me see. Make it smaller. So 0.9004 minus 0.7340. Oops, the answer was the answer. 1664. Okay, that is part A. Do you have the same answers? Okay, so when you start any examples, feel free to pause the video and try the problem first, and then continue to play the video and check your answers. Okay? So part B, find the probability that fewer than 3 of them are female. Fewer than 3. Okay, so less than 3. Alright, less than 3, but our CDF is less than equal. So 3 right here, less than 3 is less than equal to 2. I strongly recommend you to draw the pictures, okay? It can help you to make sure what is it. This is x less than equal to 2. So this be 2, and then we have 10 and 0.55. And what is that? 2 right here. So 0.0274. Okay, so this is part B. Part C, find the probability that at least 3 of them are female. At least 3 of them, so x greater equals 3. At least 3 of them are female. Okay, remember CDF is less than equal. So when you see greater than or greater than equal, think about the complement first. Complement of greater than equal of 3 is less than 3. Okay, less than 3 is less than equal to 2, right? So we already have that in part B, so 0.0274. So the answer is 0.9726. Okay, so this is the part C. So far, so good, everyone. Do you have the same answers? Okay, note. Okay, so represents n choose k equals n choose n minus k. Then the binomial distribution, this is the PMF, and let's say the p is 0.5. Well then, this is n choose k 0.5 because the probability of success is 0.5, probability of failure is 0.5. That's why we just get 0.5 to the n. And this equals to n choose n minus k 0.5 to the n. This is the binomial distribution, the probability mass function of n minus k and 0.5. Oh, let me move this to the left. Okay, then I have enough space. Okay. Okay, well, what does that mean? Well, it means the binomial distribution is a symmetric distribution. So the picture will look like this. So it's a symmetric distribution. Okay, so if p is not equal to 0.5, we actually will get skewed distribution. Okay, so here let me draw you two pictures. So this is a picture. So this is a picture when p equals to 0.2. So you can kind of see p is 0.2, so the probability of success is small. So that's why the number of success is small. So that's why the distribution skew to the close to the smaller numbers, right? So we said this guy, okay, is positively skewed, and the tail is on the right. So this is the tail. The tail is on the right. Okay, and if p equals 0.8, so probability of success is big, which means, okay, we're gonna have more success. We expect to see more success. So that's why you can see we said this guy is negatively skewed. So the tail is on the left. Okay, you can see the tail is on the left. And notice that these two pictures, they're actually mirror image of each other. Okay, everyone. Right. Let me make this smaller. Okay, let me make this smaller. Okay. Oh, right. So here I want to practice more with you how to use the CDF to compute. Okay, so here let me change a different color. How about purple? Okay, so use CDF to compute the binomial distribution. All right. Okay, so this is like all the possibilities, right? Okay, x equals to 5. Well, x equals to 5. How do we get that? Well, that's x less than equal to 5 minus x less than equal to 4, right? Okay, And then next, p of x greater than 5. Well, when you see greater than, think about the complement. Complement is 1 minus, okay, complement of greater than is less than or equal to 5. Then we're good because this is the CDF, okay? If we have x less than 5, well, less than 5 means it's less than or equal to 4. So this is just px less than or equal to 4. Okay? And less than or equal to 5, this is good. This is already the CDF, right? And then greater or equal to 5. Oh, greater or equal to 5. We first want to compute the complement because we want to have less than or equal to. So the complement of greater or equal to 5 is less than 5. Well, less than 5 is what? Less than equal to 4. So far, so good, everyone. Alright, so feel free to pause the video and compute the rest. Okay, have you finished? Okay, let's look at this. This is an interval, so it's from 5 to 11. And we don't want to include 11, and we don't want to include the 5. So which means it should be less than or equal to 10 minus less than or equal to 5 because you want to subtract the 5. So 5 is gone. So that's why here px less than or equal to 10 minus px less than equals 5. Alright, good. So the next one, 5. Now we want to include the 5. And we don't want to include the 11. What do? You have less than or equal to 10 minus, you don't want to minus less than or equal to 5 because then the 5 is gone. You want to minus less than or equal to 4. So that's why this is px less than or equal to 10 minus px less than or equal to 4. So I strongly suggest you to draw the picture because it can help you. Okay. Alright, and then here 5, we don't want to include the 5, but we want to include the 11. So it's less than or equal to 11 minus less than or equal to 5, then the 5 is gone, right? So that's px less than or equal to 11 minus x less than or equal to 5. Okay, very good. Last one, we want to include the 5 and we want to include the 11. So less than or equal to 11, but you don't want to subtract the 5, so you want to subtract less than or equal to 4. Okay, so this is what's left. Okay, so we have x less than equal to 11 minus p of x less than or equal to 4. Now you can see whether we include the endpoints or not really change the CDF values. Okay, so you gotta be very, very careful. Do we include the left endpoints? Do we include the right endpoints? I suggest you always draw this picture, and then you can figure out what are which bounds for the CDF values. So far, so good, everyone. So that is the binomial distribution. If you have any questions, feel free to ask me. Have a nice day. Bye.